This conference will now be recorded.
So, very good evening. Today, we'll be discussing about gravitational field or gravitational field intensity, gravitational potential, and gravitational potential energy. These are very important topics because depending on that, these things, we'll be able to understand the next part, like satellite, how satellite revolves around the Earth, what is the energy, what is the velocity, and also what is escape velocity, etc. We'll be able to excuse me we'll be able to understand those concepts if we learn what is gravitational field potential and gravitational potential energy. So let us start with our topic today. So first of all, let us learn gravitational field intensity or simply gravitational field. So this concept field you will learn again in the electrostatic portion of 12th standard, like in the 12th standard. See, field means what? We know field means a region of space, right? Like we have paddy field, then potato field, etc. Field means a region of space. So when you say gravitational field, what do you mean by that? Suppose you have some object of mass capital M. So it creates a field. That means its influence, the presence of this particular mass can be actually experienced by another mass, because see, any force has its field. That means any force can be experienced from certain area, certain region, in a such or in a certain region. So that region is called the field of that particular force. So here we are learning about gravitational field. Field means a region over which the force of gravitational force produced by this particular object can be felt. Okay, in other words, I'll tell you. So how do you feel gravitational field? Like if there is a gravitational field or not, how do you understand gravitational force? See, field means it is derived from the force. So if I have an object over here, I can understand whether there is gravitational field or not by the presence of another object. Okay, so that's why the the mass which is producing the field is called source field. And the mass I am using to test the presence of the field, whether there is some field or not, that is called test mass. Okay, test mass. So what is field? Field is a region around this capital mass M, capital M, mass of capital M. If we bring a certain object around this like this bigger mass having capital M is the mass. If we experience certain force, if this particular mass, small mass, is experiencing a force, then we have to think that at this particular distance, suppose it is r from this capital mass, like bigger mass, then we can say that this bigger mass has created a field at r distance away. Suppose take this as p. At P point, this bigger mass has created a field. Okay, so this is what we can say. Field means a region up to which the gravitational force exerted by this bigger mass can be experienced by another small masses. Okay, so test charge generally is to be taken very small, and most of the time unit mass has to be taken. Unit mass has to be taken as the test charge. Why is it so? Because see, this mass also, test mass also will create its own field, because this is a mass and mass can create gravitational field, because if there are two masses m and m, they will attract each other. So this also will be attracted by this small mass. Suppose this is the force on this by small m, and this also will be attracted by the same force in magnitude. Okay, so actually both can create its own field. That's why the small mass we have to take, or the test charge we have to take, test mass we have to take as very smaller mass, such that the gravitational field created by the bigger mass is not affected by the field produced by this smaller mass. Okay, so let us go with the formal definitions. So gravitational field intensity or gravitational field at any point in the gravitational field due to a mass is defined as the force experienced by a unit mass placed at that point, provided the presence of unit mass does not disturb the original gravitational field. Okay, so actually this is mathematically what it is given. How do we define a quantity? Gravitational field intensity. We define gravitational field intensity. See, I have a figure. Let us get that figure. Suppose there is a mass, like there is an object of mass capital M. Okay, then I would like to calculate the field at this particular point P, which is at a distance r from the bigger mass. Okay, so as we know, two objects in this universe, according to law of gravitation, two objects in this universe will exert attractive force on each other, and the magnitude of the force will be the same for both of them. So that force is given by g m small m by r square. This is the magnitude. Since it is attractive force, there will be a minus sign over there. Okay, so this is gravitational force experienced by this particular mass. So according to this definition, see, the gravitational field intensity or gravitational field is defined as the force experienced by a unit mass placed at this particular point. If suppose we want to calculate a gravitational field at this P point, then we have to keep a unit mass placed at this position, and we have to place unit mass in such a way that this unit mass will not disturb the original field created by this bigger mass capital M. Okay, and it is defined as the force per unit mass. Force per unit mass. So if you bring a unit mass around this bigger mass, that unit mass will experience a force, and that particular force is actually called gravitational field intensity if that mass is unit mass. Suppose in this case the force experienced by this small mass m is given as F. Okay, I'm taking the magnitude. So if we want to define gravitational field, how do you define? Suppose field I am taking as E. Generally field is taken as E. Force is taken as F. So field is denoted by E. So this gravitational field is mathematically defined as force per unit mass. Okay, force per unit mass. So if we want to exactly define quantitatively, then we have to use this mass, we have to just replace this force by gravitational force between these two, what we have got here. So you look G M, sorry, this is capital M, small m by r square. This is the force per unit mass. This is another mass m. So you look, what you get is Gm by r square. Okay, this is actually called gravitational field intensity, or gravitational, simply gravitational field. So look here, this is the gravitational field minus Gm by r square. What is r? R is the distance at, like, distance from the point where we want to calculate, like, this is the point, like, this is the distance between the mass for which you want to calculate the potential at a point P. Okay, so this is the distance between the center and this point P where you want to calculate gravitational field for. Okay, now see, this gravitational field, since we have just divided the force with mass and then we have obtained the gravitational field, so you can understand that since the force is a vector quantity, then this field also must be a vector quantity. Okay, vector quantity means what? It has magnitude as well as direction. So we have understood this is the magnitude of the gravitational field intensity or gravitational field at any point from this particular mass we can calculate. But what is the direction? See, if I write in terms of vector, this equation itself, this can be written as this. Since this mass is a scalar Rashi, so there is no change in the direction of this electric field from the force. So force and this electric field both are in the same direction. So see, gravitational force is attractive force. It will be always directed towards the center of the object. Okay, so gravitational field or gravitational force is always attractive force, and it is always directed towards the center of the object. In this case, capital M is the mass of this particular object, bigger object. Suppose this is a bigger object. So this object is producing the gravitational field, and that field will be always attractive field. So that's why the force and the gravitational field are in the same direction. Okay, and if you look the magnitude here, few points to be noted. What are the points? Look how this gravitational field, see how it is depending. It is depending on 1 by r square. That means as you go far and far and far, the field you feel is lesser and lesser and lesser. Suppose I have an object over here. Okay, it has some mass m. I'm just going away, 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 away to infinity. At infinity, what is the force? Gravitational force. At infinity, it is zero, right? At infinity, it is zero. So that's why at infinity, that means at very, very large distance, the gravitational field cannot be experienced by this smaller mass or the other object. So when one object is very, very far away from the other, then they will not experience attractive force exerted by each other. Okay, so that's how there will be no electric field intensity. Electric field intensity will be zero at infinity. Okay, at zero at infinity. Okay, so this is one thing I wanted to mention. So another point we will be able to establish here. Look what we have got. gm by r square. So this is the gravitational field I took. Let me take this as magnitude of that. Let me take the magnitude itself. Now see the gravitational acceleration. See, suppose this object. So here in this case the F is gravitational force exerted by the bigger mass is, okay, magnitude of the force I have taken, and towards the center of this bigger mass itself. Now look, if suppose this body is free to move, if it is free to move, then what would happen? This mass will move in this direction with certain acceleration, because there is a force. If there is a force, then the smaller mass would move. If it is free to move, then it will be moving towards this bigger mass with an acceleration. Okay, then small m would move towards bigger mass, towards capital M, with certain acceleration. Okay, so what is that acceleration? We can find out from here itself. So what is the acceleration? Acceleration is F by m, the gravitational force g m small m by r square divided by m. Now you just see how you get. So acceleration due to this gravitational force of attraction by bigger mass, what is the acceleration produced in the smaller mass is this one, capital Gm by r square. Capital Gm by r square. So what is this then? Look, the magnitude of this and these are the same. So we can say this to be E. Okay, E means gravitational field. So if some object is free to rotate, free to move, then this gravitational field is exactly equal to the acceleration of that freely falling or freely moving object. So gravitational field intensity will be equal to the acceleration of that freely moving body. Very interesting thing. So very interesting. So what we have understood that, so what we have got from here, look, E is equal to A is equal to Gm by r square. That means the gravitational, see, intensity of gravitational field at any point is equal to the free acceleration produced in the freely falling body or freely moving body freely moving body. We can just prove it. Gravitational moving body. We can see one interesting point over here. Very interesting point will be cross checking here. See, intensity of gravitational field due to earth, what it is. We'll see gravitational field intensity due to earth, what it is. Okay, so we have been considering the earth to be a sphere of mass m and radius capital R with uniform mass density. Let us say with uniform mass density. Density rho. This is the assumption we are making. Okay, if we require this density, we will make use of it sometime. So this is, suppose this is the earth, and there is a small mass just r distance away, small mass m r distance away from the earth. So according to the definition of the gravitational field intensity, see, the earth will produce a field at a distance small r, so that gravitational field can be written as gm by r square. Okay, gm by r square. Suppose this is the point P where we are calculating the gravitational field due to this earth. And you know, like earth applies a gravitational force of attraction on any object towards its center, right? Towards its center. So that force is given by gm by r square. Okay, and force per unit mass will give you the field intensity. So this is what is, suppose this is having equation number 1. Now look what we know, that if this small object is here, just on the surface, okay, if the object is just on the surface, then we can write the small r is equal to capital R, right? So I can write gm by capital R square. And one more thing, look, we know from previous classes, we know that gm can be written as g into r square at the earth surface, at any point on the earth surface. Okay, at any point on the earth, on the surface of the earth, we know gm is equal to small g into r square. Small g is actually the acceleration due to gravity. Okay, so this is what, if we apply over here, look what we get, g r square divided by r square goes off, and see what we get. So on the earth surface, what is the value of gravitational field intensity? On the earth surface, gravitational field intensity is nothing but equal to g. It is equal to g. G is what? This is the acceleration due to gravity for any falling body. For any falling body, the gravitational acceleration due to earth is small g, and that is actually equal to the gravitational field intensity on the earth surface or near the earth surface. Okay, so near the earth surface, so see what was the corollary previous slide, what we have learned, that any freely falling body or for any freely moving body, the gravitational field intensity can be obtained as the acceleration of that freely moving body, which is produced by the other body. Okay, other body. So that is the acceleration due to the gravitational attraction produced by a bigger mass on this unit or the smaller mass. Okay, so gravitational field intensity at any point can be expressed as, or it is actually the acceleration produced in the freely falling body. Okay, now using this corollary, what we have understood from here, due to the gravitational field intensity or gravitational field due to earth, we have learned this is the gravitational field due to earth. Okay, and if this body is freely moving or suppose freely falling body, then for that we have proved here that the gravitational acceleration or acceleration due to gravitation will be exactly equal to the gravitational field at that point, field intensity or field at that point. How do we get that? So see, this is gm by r square at the earth surface, at the earth surface. at the Earth's surface, that means small r is equal to capital R. If we put in this equation 1, then we get Gm by capital R square. Now, at any place or any point on the Earth's surface, we can write Gm is equal to small g into R square. That means small g is the acceleration due to gravity into R square. R square is the radius of the Earth. So if we put this also in this equation, then what we see? We see that E is equal to g, small g, that is the acceleration due to gravity. So for a freely falling body, gravitational field intensity near the Earth's surface or at any place on the Earth's surface is nothing but the acceleration due to gravity, and that is sometime it is written 10 meter per second square or 9.8 meter per second square. Okay, so this is the thing. So we have learned what is gravitational field intensity and what is gravitational field intensity on the Earth's surface, and how we can understand that the gravitational field intensity on the Earth's surface for a falling body is nothing but the gravitational the acceleration due to gravity. Now we'll learn what is gravitational potential energy. Okay, so this is very interesting. So potential energy means what? What is the potential energy? We have already discussed, I think, in the kinetic energy and potential energy part. Okay, so potential energy is actually the energy. Potential energy is due to the configuration and position of certain object at any point in the gravitational field. Okay, gravitational field. So potential energy you have discussed already many times in the kinetic energy and potential energy, that chapter, like work for energy chapter. So potential energy is actually arising due to configuration position of certain object at any point in the gravitational field. So we had seen many examples on that. So now today we'll actually calculate mathematically what is gravitational potential energy. Okay, let us see what is the formal definition. So gravitational potential energy of a body is defined as the energy associated with it due to its position in the gravitational field of another body. Suppose you have, so you know, like what happens when there are two bodies in this universe, they will be actually exerting, like when they are like considerably close to each other, they will interact through gravitational forces. Okay, through gravitational forces. So they will interact through gravitational forces. Suppose you have a mass m1 and m2. If they are not very far, if they are not at infinity, then at least they will talk to each other. That means they will interact with each other through interact each other through gravitational force. Obviously gravitational force or field, actually by the field they will interact. Okay, all right. So we have learned what is gravitational field in the previous discussion. From the previous discussion, now we'll see what is gravitational potential energy first. So gravitational potential energy is that when there are two objects in this universe, they come closer to each other, they interact through gravitational force. And see, if we just move this object either here or move away, then look, since they have an interacting force between them, gravitational force between them, we are doing two things. Suppose this is M1 and this is M2. So this will be actually attracting, this M1 will attract this M2 body, or M2 will attract the M1 in this way. Okay, they will attract towards each other's centers. That means there is a force acting between them. Now if you move this object somewhere, then what you are doing, you are actually work, like you have to do certain work, certain work against the gravitational pull, right? This is actually pulling this M2, but we are just taking it away. That means it is against the gravitational pull. Okay, so you have to do certain work, and this work will be stored in this object M2 at particular position, as potential energy. That is called gravitational potential energy. Okay, now if you do other way, if you just move the object in this way, then you look, the gravitational force is actually helping you to pull it here, right? Then you have to do certain work against this gravitational force to keep it here. Okay, here also you have to do certain work. That's why when you take it away or towards, okay, then you have to do certain work on this object, and that will be stored as gravitational potential energy at any particular point in the field, in the gravitational field of the other body. Okay, now we'll see. So we have learned what is definition of the gravitational potential. Okay, so it is actually measured as the work done in bringing a body from infinity. So suppose like gravitational potential energy you want to calculate. So gravitational potential energy is actually defined as, work done. See, work done means F into dx, and it is, see, infinity to brings up to certain point r. Okay, so this is the expression for the gravitational any potential energy. In fact, in this case we are just using as gravitational potential energy. Okay, all right, so this is the work done in bringing a mass from infinity to at the particular point. Okay, so suppose, okay, I'll just make it much more clear. Suppose you have an object over here having mass capital M. Now from this object at smaller distance away there is a point P. So there you have to find out what is the potential energy. So to do that, what you have to do, you have to bring one unit mass. Okay, sorry, not unit mass, another mass, any mass you can take, another mass, small m. Suppose it is situated now at infinity or at very very large distance. If you bring this mass to this point, then what is the work done against this gravitational force or by the gravitational force? So that particular work done will be the potential energy stored in at this particular point. Now look, mathematically it can be written as this. Okay, so work done from bringing it, bringing it from infinity to certain point r. Okay, so this is the definition, mathematical definition. Now what we'll do, we'll calculate the gravitational potential energy, for like expression for the gravitational potential energy, and then we'll see for earth and all those things. Okay, so let us suppose this is the earth. Okay, so gravitational potential energy of earth we are going to calculate now. Let us first find at any point, this is the point A. Suppose, okay, I have, see, in this case also the general consideration for the earth has to be made. Suppose the earth is a perfect sphere of radius capital R, and it has mass capital M. So these are the assumptions we are making every time. So now look, from the earth surface, this is the surface of the earth, surface of earth, and from earth surface at certain distance R, okay, sorry, not from the earth surface, it is from the center of the earth. See, a point is at a distance r, small r, okay, and at this point, if there is a small mass m situated over here, then what will be the potential energy at this particular point A? So that is the problem here we have to solve. So for doing that, let us suppose this small r is much greater than the radius of the earth, okay. And now what you have to do, suppose at an any instant the object is at a distance this p, at any point, any time it is at x distance away from the center of the earth, and it is situated at p. So let us suppose small m is situated at p, which is x distance, which is x distance away from the center, away from the center of the earth, okay. So at any instant it is situated over here. Now what you have to do, you have to find out what is the force when the object, this mass small m, is situated over here. What is the force, gravitational force exerted by earth in the direction towards the center of the earth? So what is that force, gravitational force? So that can be easily obtained, that is g capital M small m by the distance square between, so this is x square, okay. This is the gravitational force at any instant this particular object experience, okay. Now look what we are doing, we are just bringing that object small m to this q by a distance, how much, dx distance. This q is dx distance away from p, so this much displacement we are making, okay, this much displacement we are making, okay. So what is the work done in this case, what is the work done? The work done will be suppose dw is the work done, so this is f into dx, so this is the work done. Now see how we can write f into dx. So dw work done is equal to f into dx, and what is f here, g m by x square into dx, okay. So this is the work done. Now what is the, so this work done is the potential energy, right? This work done is the potential energy stored at this point. Now if I bring, so this is the potential energy, this is the potential energy at this particular point, okay, at p now, okay, at p, sorry, at q, the potential energy at q is that. Now see, if we want to calculate the potential energy, the whole potential energy at energy at A, which is actually r distance away. OA is equal to small r. So at this distance, what is the work done? What is the potential energy that you have to calculate? By the work done to bring this particular mass from infinity to that point r. Okay, so what is the work done? dw. Okay, you have to integrate it. So dw we know, we can just put it here. So gmm, these are constant, so we can write this as infinity to r, the dx by x square. Now if you integrate it, what you get is this will be minus 1 by x infinity, and this is r. Okay, so lower limit and this is upper limit, so you can see from here that you will get gm small m by x. I'm sorry, this is r. If you put the value of the upper limit, this is the potential energy minus gmm by r. Okay, so this is the potential energy we obtain. Okay, so where we obtain, this is the potential energy at any point r from the earth surface, sorry, from the center of the earth. This is the small r is the distance of the point P where we want to of the point A here, in this case of the point A where we wanted to calculate the potential energy due to this earth. So we have got it. What is that? This work done, this is called potential energy, which is denoted by U. So this is the potential energy. What is that? Minus G capital M. This is the mass of the earth. This is the mass of the object divided by R. So this is the one we get. So we can write this according to definition. This is the potential energy, Gm small m by R. This is gravitational potential energy. Now see here, there are few things we have to remember, that see, when R increases from 0 to infinity it goes. So how it is doing now? See, this also decreases, right? This decreases. Gravitational potential energy decreases, isn't it? Potential energy decreases, and see, at infinity U will be 0, and this 0 is zero line is called the reference or zero level. Zero level. This is called zero level. So R is equal to infinity is called zero level, because there the potential energy becomes 0. Okay, zero level, or that is called reference for gravitational potential energy. Reference for gravitational potential energy, infinity. Generally, in case of measurement of potential energy, you should have a reference point with respect to which you have to calculate potential energy, whether it is gravitational potential energy or any type of potential energy. So this gravitational potential energy, so reference for gravitational potential energy is infinity, because their potential energy is 0. Generally, potential energy is taken at 0 at the reference level, and then we calculate the potential energy with respect to that line. Okay, now we'll see one more interesting point, that so gravitational potential energy, so there are few important points we have to remember. Look, the point number 1. So in this gravitational potential energy we see, so let us write gravitational potential energy as PE itself. So gravitational potential energy is given by Gm small m by R. Okay, so what does this mean? This negative means this is the potential created by potential energy produced by attractive force. Okay, force field associated with this potential energy is called attractive force field. Force field is attractive in nature. So that is what it is meaning. As the distance increases, the gravitational potential energy also increases because it becomes zero. See, as r increases, r increases, as r increases, potential energy also increases. That means, suppose r, see, in the beginning it was potential energy g mm by some 2 meter. Okay, now if we increase this g mm by 10 meter. Okay, see this value, since there is a negative sign, this is actually greater than, so this is greater than the earlier one, minus g mm by 2. And in fact we have seen at infinity r is equal to infinity, the gravitational potential energy is 0, that is greater than any negative quantity. So gravitational potential energy at r is equal to infinity is 0. So this is also bigger value than any negative values. So that's what it is. So if the potential energy increases, sorry, r increases, then the potential energy also increases. Okay, so we have discussed 2 points. I'll just write the second point. One is negative sign, so which indicates that the potential is derived, or potential energy is due to the attractive force field. And now, so potential energy increases with increasing r. Okay, that is what we have learned now. Now see, if you want to calculate, see, we know the potential energy. So u, let us write u is the potential energy, g m by r. Okay, so if we want to calculate the change in the, want to calculate the change in the potential energy. Okay, I'll write here in short, potential energy in bringing an object, potential energy in bringing an object from r1 to r2. Okay, r1 to r2 we are bringing. Let us go here. So I am here. See, there is a gravitational potential, the gravitational field over here. The whole reason there is a field. So suppose I am here somewhere at r1. I want to bring this object. Okay, there is an object. I am bringing that to somewhere here at straight line distance. Okay, so let me draw it parallel, a horizontal line. So I am just at r2 distance away from the original object, which is producing the potential energy, or the potential, or the, sorry, or the field at r1 and r2. So I am bringing an object. Okay, r1 to r2 or r2 to r1, whatever. So in this case, the potential energy, if you go to the original equation, so there also you will find, see, the total energy, see, total work done was written as infinity to the particular point, and then the work done, small work done, which was g m small m by x square dx. This is the original expression. Now in this case, look, I am bringing an object from R1 to R2, R1 to R2. So here if you do the integration, what you get? You get G capital M small m by 1 by, see this, if this is small, then 1 by R1 minus 1 by R2. Okay, so this is the 1. Okay, so this is the 1 we get. So this is the change in the potential energy. So sometime you will be able to solve using this problem. See, there is, see in the satellite, maybe like there is a satellite which is revolving the earth, okay, at certain orbit. If we want to calculate, like if we want to send this satellite to some other orbit, so how much energy has to be provided? So that is the change in the potential energy or difference in the potential energy from R1 to R2. Okay, R1 to R2. So that is what you have to calculate. So change in the potential energy, in that case you have to calculate, and that much kinetic energy has to be given to, or that much energy has to be given to this particular satellite to go into the other orbit which is greater than R1. Okay, so in that case you have to calculate the potential energy. And look, this minus sign depends on like which one is greater and which one. So this will be either positive or negative. That means you have to either take away energy or you have to provide certain energy. Suppose there is a satellite over here. If you want to bring it back to R1 itself, then you have to withdraw the potential energy, or sorry, withdraw the energy. Okay, and what is the amount of energy you have to withdraw? That is the difference in this, or change in the potential energy you have to withdraw to bring it down to the previous orbit. Okay, so this is an important concept to be understood. So now we'll see what is the gravitational potential energy for, okay, so we'll just see gravitational potential energy on the earth surface. I'm sorry, if we suppose we are on the earth surface, we just lift any object to height h from the earth surface. So this is the center of the earth, this is r, this is the height. You are just taking an object from here, so mass m to here, you bring it from the earth surface to here. Excuse me. So in this case you have to calculate what is the potential energy at this particular position. So you have to calculate that. See, if a body is moved from the earth surface to a certain height r, so in this case, see, we knew that the change in the gravitational potential energy was, like, expression for that is delta u is equal to gm small m into 1 by r1 by 1 by r2. So see, I'm bringing this object from earth surface to this particular height. So we have to always actually see the distances r1 and r2 from the center of the earth. So r1 is actually r and r2 is here r plus h. Okay, now what is the change in the potential energy? Let us say this is 1 by r capital R and this is 1 by r plus h. Okay, now look, what we get is, if we do a little bit of simplification, then gm small m by r 1 minus 1 plus h by r. Okay, this is the point we get here. Okay, now look, if we take it, see, as we have done in the calculation of gravitational acceleration in any height, so what we had done, we had taken it to numerator, and if this height is much less than r, then this can be expanded by binomial expansion, and then we can neglect the higher term, higher order terms or higher power. Then see, what we get is 1 minus 1 minus h by r. Okay, so now this is nearly equal to m gm small m by r. This get cancelled, this will be plus, so h by r, right? So what we have got, change in the potential energy. This is G capital M. This can be again replaced on for the earth surface with G r square. G r square. Look, this r will get cancelled with this r. So what we get is here, so G mg into h. Okay, mgh. Okay, so what we get, the change in the potential energy, that is the mgh. And if we see, if we just take the potential energy to be zero at this level, then what is the potential energy here at this height h? That is mg into h. This is what we have discussed in work power energy chapter, right? I hope you remember this. So generally on the earth surface, the so if we just take any object from earth surface to certain height, the change in the potential energy will be mgh. And if we take the earth surface to be with zero potential, then this change itself can be told as the potential energy of this object at this particular height will be mgh. Okay, that means if you take any object of mass m to a certain height h from the earth's surface, then the potential energy at this height will be mgh. So this is what we have discussed, if you remember. I'll stop it here for today. Potential, gravitational potential, or let me just quickly tell you what is gravitational potential. So gravitational potential, then we will stop it. Okay, I'll take another 5 minutes. What is gravitational potential? See, we have learned what is gravitational potential energy, that is U is equal to minus g m by r. Actually, gravitational potential is defined as the work done per unit mass. Gravitational potential, if we denote it by V, then it is defined as work done per unit mass. Work done per unit mass. Suppose you have an object over here, capital M, okay? Then you want to calculate at certain distance r, you want to calculate what is the gravitational potential over here. So to do that, what you have to do, you have to bring a unit mass to this particular point where you want to calculate the gravitational potential. From where you have to bring, from infinity to that particular point P. Okay, then what is the work done? The work done itself will be called as the potential at this particular point. So if we define it with a nice language, let us see what we can say. The gravitational potential at any point at any point is the potential energy associated with a unit mass, energy associated with a unit mass. Due to its position in the gravitational field. in the gravitational field of other, field of other. So it is, see what we know about potential energy. The potential energy is the work done in bringing an object from infinity to a particular point in the gravitational field. So if this is the work done, then work done per unit mass is called the gravitational potential, right? So if we write gravitational potential, see we know the gravitational potential energy is this by r at certain point. Suppose this is the mass m at this particular point, which is at r distance away. The gravitational potential due to this mass will be g m small m by r divided by small m. So this, if this is the small m over here, okay, so this small m goes off, then you get actually g minus gm by r, okay, minus gm by r. So this is the gravitational potential, okay. So this gravitational potential has unit, so this is work per, see work done per mass, that means joule per kg or arc per gram, okay. Now due to earth, how do you calculate? On the earth surface, how do you calculate? So on the earth surface, this gravitational potential will be v at small r is equal to capital R, that is the radius of the earth. So we can get this as gm by r, okay. Now this is the actually gravitational potential on the earth surface. So this is gravitational potential on the earth surface, okay. So this is the expression for gravitational potential on the earth surface. Now what is the relation between u and b? Relation between gravitational potential and potential energy. Gravitational potential energy, and so energy is u and gravitational potential that is b. So what is the relation between them? So see from here you can easily write. So we know u is minus gm small m by r, and we know this much is the gravitational potential. So you look, gravitational potential into the mass is actually called the potential energy, okay. So what you get, gravitational potential energy is equal to gravitational potential into the mass. So this is the relation. U is the gravitational potential energy, which is equal to excuse me, gravitational potential into the mass, okay. So this is the relation, okay. So with this we will stop it here, and in the next class we will be learning very important and interesting things about satellite, geostationary satellite, escape velocity, etc. So bye for today. Thank you for your patience.